Hi everyone, thanks for coming. I'm Niklas. I work at Spotify and I'm gonna tell you a little bit about work that we've done over the last, year or two around automating how we do software maintenance and so on, and a little bit around the learnings from that. Hopefully should be interesting, hopefully should be applicable. Also, if you're maybe a slightly smaller company than we are, I think some of the learnings, we started a bit late, so I think some of these learnings might be useful also when you're earlier in your growth as a company. I'm happy to take questions. I'm going to save some time at the end for questions, hopefully, if I don't run late, but I'm also happy to take questions in the meantime. So just raise your hand, and I think we have a microphone that we can send around. Cool. So first of all, let's take a little bit of a step. Oh yeah, there's a few seats in the front. I think you can probably get squeezed in. So first, let me take a little bit of a stab of reasoning around what Spotify actually looks like. I'm not going to spend a lot of time on this. I'm happy to take questions if you have any. I just wanted to speak like conceptually what the architecture looks like. So we have what you would probably call a microservice architecture. Our architecture sort of preceded that term, but we have started using it. Wasn't that we were particularly like smart or future were able to imagine the future. It just made sense for us to start building things with like fairly small components that had a single purpose, that we could scale independent of each other, we could own them independent of each other. And in fact, what we've done, oh, sorry, that wasn't what I intended to do. What we've done is to apply this to all types of components, not just backend services. So at Spotify, if there's a data pipeline, if there's a mobile feature, if there's a website, they're going to typically be these fairly small self-contained components that are owned by a single team. And we built our entire architecture around that. So if you build a website to Spotify, there's this whole like routing infrastructure to be able to get requests to your particular component if you own a part of our website, for example. So we have a lot of these different types of components, and it might look like this. I'm not going to spend a lot of time explaining this, but you can see this like green layer of all of these components. These are the main things we're going to talk about today. They're actually deployed, as you can imagine, to make them actually useful. So each component might exist in many, many replicas. So if you imagine a backend service, we might have a few replicas for some internal tool or whatever, and we might have hundreds or thousands of replicas for the most loaded, heavily used backend services. Again, same is true for other things. Just for us humans to be able to reason about all of these components, we then group them into what we call systems, and each system is owned by a single team that we call a squad. So a team is, 5 to 12 engineers, something like that. They have a mission, like our team, we're building the best search experience possible for audio, or we're building the best playlist experience possible. And they decide and design and build and implement and operate their own components. And of course, as we've done this for about 15 years now, it's getting a bit complicated. So this is the dependency graph for our production backend services. There's a few thousand nodes in there, and you can see each line in this is where one service is calling another service. Again, we're not going to spend a lot of time on this, but I wanted to show this to sort of speak to the complexity that you get to. And it might look, and I think it would be reasonable to think that this looks fucking insane. Like, what the hell are you people doing? So just to sanity check that we're not that insane, this is the number of services from a bunch of different companies. These are just numbers that I either found in some blog post or heard from some friend at one of those companies. As you can see, we're roughly on par with where other companies are. So it's not that Spotify is doing something particularly stupid here. This is what a large-scale microservice architecture looks like these days. There's a different dimension to look at this, and that is to look at the growth over time. So this shows the purple line, the purple area here shows the number of components that we have. In our case, they happen to be registered in this developer portal that we have called Backstage that we've open sourced and you can use if you want. So that's where we register this. And this is just the number of such components that we have registered. For some reason, there's not a y-axis on this, but I can tell you that the maximum on this is around 40,000. You can extrapolate that graph. And the small kink at the top is just a cleanup that we did recently of some test components. You can see that the trend is pretty clear, like it's growing, 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 growing. The blue line shows the number of engineers that we have. And you can see that that's not growing as quickly, which is a good thing in many ways. We're able to keep our developers productive. They are able to build new features, build experiment. So yeah, this also, I should mention, this is not just production components. This also includes experiments we're running or hacks that some engineer has done. So this is everything. But it's good, like we're seeing that our engineers are able to do a lot of work and try out many new things, which is exactly what we want. The flip side of this, of course, is that as an engineer, you have more and more stuff to maintain. If there's a security patch and you need to apply that to all your, let's say, backend services or mobile features, you might have many of those that you own in your team. And that becomes pretty boring and arduous after a time. So one way of looking at this would be to look at what maintenance and migrations typically look like. And this is just an example. This happened to be, so when it comes to our backend, we're mostly run a Java-based backend. So this shows the adoption when we moved to Java 11 a few years ago. And as you can see, this took us almost a year or 9 months. It took a dedicated team to do this. They sent out more than 2,000 pull requests to our teams to do this migration and tracking down this and doing a lot of, project management and nudging people and reminding people and all that stuff. That means this is a lot of effort to do one of these like fairly simple things, should be a fairly simple thing. And it meant that we could only do a few of these per year. If we would do lots of these, our engineers would push back and say, hey, I have an actual work to do. I can't be migrating Java versions all day. So we figured we're going to have to deal with this. We estimated we could maybe do like 10 of these migrations per year, which was probably not true. We could do maybe more like 5. And we wanted to get to at least 100 so that we could much more actively maintain our software ecosystem. So that was the goal that we set out for ourselves. And the way that we imagined doing this was rather than think about our software from a component first mindset, which is what we had done forever. So again, when we did the Java 11 migration, what we did was we sent out a document to everyone saying, here's how you take your backend service and migrate that from Java 8 to Java 11. Please do this. And then we had developers do that for thousands of backend services. What we wanted to do now instead was, how about if we think about our entire fleet of components and how we can apply operations to that fleet, to mutate that entire fleet as a whole. And we call this a fleet first mindset. So this is what I'm going to talk about today. So one easy question to ask here is, if you have, so yeah, I forgot to tell this part of the story. So I said that we have thousands of components. We have around, if I'm going to continue using the backend service as an example, we have around 4,000 or 3,500 backend services, I think, distinct backend services in production. Most of those live in a Git repo on their own. So that means that we have thousands of Git repositories that contains production components. One way to solve this problem, you could imagine, would be, how about just move that all into one repository and you can make atomic changes to those components. Turns out that that is a valid answer or partial answer to this challenge, but of course it's slightly more nuanced than that. Polyrepos versus monorepos, both of those has a lot of benefits and drawbacks. We are gradually moving towards a monorepo world at Spotify, but it's taking a lot of time. It's very complicated. We are there when it comes to our mobile apps, so we have these mobile apps repositories with millions of lines of codes, and that has a certain set of challenges versus our thousands of polyrepos. But we wanted to solve this problem more quickly than we could move to a monorepo. And even if we were in a world of having a monorepo, you actually still have a lot of these challenges. Even if you're able to make an atomic change in Git, you probably don't want to roll that out as one big atomic thing where you deploy thousands of backend services at the same time, or deploy thousands of or tens of thousands of data pipelines at the same time. You need to make those rollouts orchestrated. You might not even be able to do an atomic Git commit because you might have hundreds of teams that needs to review your change. And if you're going to wait on that atomic commit until that last 200th team have done the review, you're going to be waiting for months. There's a great paper from Google, which famously has a very large monorepo and is extremely experienced with operating that, where they, I think in this paper, they did this API refactoring that I think affected, if I remember correctly, 3,500 files or something like that. And they had to break it down into many, many, many small change sets to get each of them reviewed and merged, and then orchestrate the rollout of that in a safe way. So the tooling that I'm going to talk through today turns out will probably be pretty similar in a world where we have a monorepo compared to where we are today. All right, so the problem that we're taking on is both a technology one. That's where I'm going to spend most of the time talking through what we've actually built. But it's also a bit of a cultural one. I'll talk through that as well. There's a change management part to this, and I'll talk through that as well. But let's start with the technology one, and let's look at what one of these fleet-wide changes looks like. So again, quick reminder what I said before. We want to make a change that we can apply to thousands of repositories, make that changes in a coordinated and controlled fashion, and roll that out in a safe way. That's the goal here. So it's as always a bit more complicated than this, but I'm going to reason about this in these like 4 fairly high-level steps. So first of all, we need to identify where we need to make changes in the code. We need to have some way of authoring or making those changes. We need to make lots and lots of pull requests. Again, we use Git, so we need to change. There are a few seats if you want to squeeze it. So we need to send out lots and lots of PRs. And then lastly, we need to orchestrate the rollout in a safe way so that if things starts breaking, we can pause and roll back and whatnot. I'm going to reason through each of these in order. If we look at the sort of identifying where we can make changes, the simple way of doing this is through some sort of code search. And I think we probably all have this. It might be part of your, if you use GitHub, you get that out of GitHub. You can use SourceGraph. There's lots of these tools that can enable this in a good way. And we have those as well, of course. They're usually pretty coarse-grained, but they work fine for a lot of use cases. So you can identify like, where do I have something that looks like this piece of code or this piece of configuration? And then I know that it's those repositories that I need to make changes to, or those paths and repositories that I need changes to. In our case, we have also ingested all our code, our configuration, and a ton of runtime instrumentation into BigQuery, which is this tool that Google has that you can do ad hoc querying like SQL on top of data sets. So that means that we can actually do much more fine-grained targeting. So you can do much more complicated matching, and you can join with various parts. So I can say, hey, I only want the source code for components that are of this particular type, so I can join it with my backstage data, or I can join it with, I only want to do this with components that has a certain number of replicas in production, like all those types of things. So that has turned out to be a very powerful mechanism for us, and something I can generally recommend to look into to do. It doesn't have to be BigQuery specifically, but having good instrumentation and putting that into some sort of analytics tool or database where you can query it is a very powerful mechanism. The last, and we don't have this yet, it's something that we're currently building out, is what is typically called semantic code search. So this is where you index your code so that you can start looking for example, where you have API calls. So if you imagine we have a library, it's used in hundreds of components, where is a particular method of that library called? And this is of course very useful if you want to do API refactoring, for example. You could target much more specific. And there are open source tools like Kite from Google that can do the semantic code search, but it's challenging to do at scale. So we're still working on getting this in place. The BigQuery stuff has been very powerful in the meantime. All right, now we need to, so now we know where we need to make the change. Now we need to actually have something that can make the change. So the way that we do this is we implement what we call a code mod, or actually, typically our nomenclature is a shift. And this is just, in our case, a Docker container that you run on a local clone of a repo, and it does the change that it needs to do. And that's it. So these are typically very easy for simple changes, these are very easy to write, and we have a bunch of already ready-made containers. So if you need to change, some YAML file, you can do that with a ready-made container and just provide some configuration for it. And the more advanced you get, and in particular, once you get into wanting to refactor code, things get pretty hairy pretty quickly. And there's this law again coming out of Google called Hiram's law from an engineer called Hiram Wright, which works on Google's team that basically builds the same type of tooling that I'm talking about here. See, he put up this law. I think he sort of made it as a joke, but someone else in that team then published it and whatnot. And it basically says that, yeah, you can have your fancy API and you can have your documentation saying how that API is supposed to work. But in reality, once you have enough people using that API, every possible observable behavior of that API, someone will depend on. And this is super annoying when you actually try to change things at large scale. And we spoke to this guy when we started this work, and he told us, like, yeah, you're going to run into this stuff. It's going to be annoying. And yeah, to no one's surprise, it turns out that he's absolutely right. And we see this all the time. And again, you can imagine sort of the broader your API surface is, the harder this gets. So if you're changing a YAML file, it's fairly straightforward. There's still a lot of nuances to doing that as well. But once you get into actually trying to do a semi-advanced refactoring of some Java code, it's tons and tons of code to actually do that change. Because you're going to run into all of these weird edge cases where people use your stuff in ways that you never imagined. But there are some frameworks to help a little bit with this. So we use all of those that are listed here. The Shifty one is our internal one, so it's not published yet at least, but we're in particular heavy users of Rewrite, which came out of, I think, Netflix, which is just a Kotlin Java library for basically making code refactorings. And there's a bunch of these available that were in addition to these that we use as well. But this turns out to be actually the hard part of this problem, and we're still learning how to make more and more advanced changes. I'm going to do a quick aside here. So one type of change that you want to do, that we want to do at least, is of course to our cloud resources. So we happen to run in Google Cloud. It doesn't much matter which cloud you run in, or if you run on your own on-prem, you probably have a lot of resources in there. That might be accounts or databases or buckets, or in this case, a caching cluster or whatever it might be. And in order to make changes to this, you need to have them in Git somehow, of course. A very common way of doing this is using Terraform or Ansible or a tool like this. And we do this well. In our case, we use a Kubernetes-based tool. And there's a few examples shown here of what that might look like in our case. The reason I'm mentioning this is that when we started this work, we were actually sort of halfway or just beginning the transition into this new tool from a pretty messy state of having some stuff in Terraform, a lot of manually created stuff as we had moved into or migrated to cloud a bunch of years ago. So in order to actually make it possible for us to make these fleet-wide changes to cloud resources, we needed to finish up that migration. So that was a big part of the job that we did, was to actually do that. I just wanted to call that out as again, if you want to be able to make these large-scale fleet-wide changes, you need to have your stuff in Git, somewhere where you can actually modify it in a safe way. So the next part that we then built is called Fleet Shift, and this is the orchestrator. So what you do is that you have your Docker container that makes that change. It makes, as I said before, it makes a change to a single repository. You've figured out your targeting, so you have a number of repositories, and that might be anywhere from a few to thousands of repositories that you want to apply changes to. And now you need to combine these two, and that's what Fleet Shift does. So Fleet Shift is an orchestrator. What it will do is basically check out all the repositories that you're making a change to locally. For each of those, run the Docker container in a orchestrated and coordinated way. And then look at, when I ran this Docker container, did that create any change, any diff? And if so, it creates a pull request based on it. And this can run once, so you can have your shift and you run that once if it's a one-time change you're doing, or you can run it scheduled. So for example, we update all our dependencies. So if you're used to using something like Dependabot or Renovate or similar, we use this to schedule those types of jobs. So they run every day. So every day there's one of these shifts that come around and look at all the Java services, for example, and check if they need to update any of their dependencies. And if so, create a PR and send that to the owning team. And as a shift author, if you're one of the people who are making one of these changes, you can go in, and this is actually just a way to sort of debug your shift. Is it working as expected? So I can go in there, see the output from it. I can see what diff it created for some particular repository in this case. And here's a good example of one of these cases where we actually wanted to change a cloud resource. So here's a shift that runs continuously and does cost optimization for our big table database clusters. So it will do some analysis on the load of this cluster, and it will configure the autoscaler for that big table instance and send a PR to the team. And the PR will look something like this. So this is what if you happen to own one of these big table instances, you will get a PR saying something like this: hey, we discovered that we can configure your autoscaler in a better way. Here's the PR to do that. Hopefully that makes sense. So now if we put ourselves in the shoes of the team, I don't remember which team it was, Taylor, I think was the team that, oh, sorry. Yeah, Taylor, as you can see on the top there, is a squad at Spotify. They have received this PR. But if you put yourself in the shoes of those teams and you imagine yourself receiving hundreds of these automated pull requests, that's going to get pretty fucking annoying pretty quickly. And we don't want that. We don't want our engineers to have to review all of those changes. That wasn't the purpose of this work. It wasn't to make more work for our developers. It was the opposite of that. So what do we put in place? And this is maybe the most potentially controversial part of what we're doing, is that we have something that we simply call auto merging. So for most of the shifts that we do, not all of them, if they are particularly risky, we will not do auto merging. But for most of the ones we do, as long as your CI build is green, we will come around and merge that PR without any human review. So we have an auto merger that basically goes around, looks for all of these Fleet Shift PRs that we've generated, see that they look safe. It applies a bunch of rules, so we only auto merge during office hours. We don't auto merge on holidays or whatever it might be. We might wait for a while, so to allow for some particular shifts, we say to the team, hey, you have 2 weeks to do a manual review of this, and then we're going to come around and auto merge it if you haven't already merged or closed it. So to give teams some ability to review. But in the end, for more than 75% of the PRs that we send out, we end up auto merging. So this brings us to this question of culture and like engineering culture and practices and whatnot. So when we started this work, or maybe let me take a step back. We have a very long history and very strong culture around ownership. So I mentioned early on that each component is owned by one of our teams, and that team has full responsibility for that component. So, and you as a team, you figure out which backend services or which pipelines you need, you design and you build them, but you also operate them. So you're on call for those components. So you are the one who's waking up in the middle of the night when things break. And you have also always been fully in control over those components, every change that goes into it. You as a team, because you own that component, you own the repository, you've been the reviewer of every change that's gone into that component. But now all of a sudden what we're saying is that no, for these fleet-wide changes, it's going to be someone else somewhere far away in the company who makes one of these fleet-wide authors one of those changes, and then we're just going to auto-merge that into your repository. Good luck, have fun with that when that breaks in the middle of the night. So we imagined that this was going to be a big change for us, and we were going to get a lot of resistance from our teams. Turns out that wasn't at all the case. Turns out the developers just liked getting this work done for them and not to be bothered. But we did a lot of discussions with our engineering teams and whatnot to prepare for this. In the end, it turns out to we're super happy as long as you don't break stuff. If I can have less work to do, awesome. I'm gonna like that. But of course, we did need to prepare ourselves a little bit. So, for example, we had some components that didn't have great test automation. Generally speaking, we had pretty good test automation, but there were a few types of components where we had less good automation. So we had to ask our teams to please make sure that the things you care about are under a test. This is typically called the Beyoncé rule. Well, you will see Beyoncé on the slide. So if you like it, you should put a test on it, I think is the rule. So that was essentially what we said to our teams. Make sure that whatever needs to work in your software, that needs to be discoverable as part of the CI build, or we're going to merge it. And of course, you know this as developers, you can't really figure out all of the possible failure scenarios up front. So a lot of this has been more incremental of yes, we have broken things. But then it needs to be a discussion with that team of maybe you need to add a test to be able to catch this in the future. So this is very much a continuous thing that we're doing. And we have a tool, this is part of Backstage, that we call Soundcheck. And Soundcheck is a way to, basically you can run a bunch of validation checks on a component and say, hey, does this component have a good integration test? Does it have all its resources defined in our declarative infra as I showed before and so on. So we defined one of those called Soundcheck programs for fleet management as a preparation for fleet management to allow teams to self-assess themselves. And we left it to the teams. So if you as a team decide that, no, we're not gonna apply that, we're not gonna prioritize improving our test automation. We think it's good enough, then that was fine. We left it to the team to decide, but we gave them the tool to self-assess themselves in Soundcheck. So then let me speak about where we are. So this is I mentioned before, this is very much ongoing work. We have a few teams that are working very much on this at the moment. Essentially what we did during last year was to roll this out to the vast majority of our fleet. And we're focusing on, I'll tell you where we're going in a second. So we have to date done more than 130 of these fleet-wide changes. I think this number is actually slightly outdated. It's a little bit higher now, but not significantly so. And we've sent more than 500,000 automated PRs. Again, most of those are auto-merged, so it's not as horrible as it might sound. And the list here, I won't go through that, but the list here shows the type of changes that we're doing. So I mentioned that we bump dependencies every day. So if there's a new dependency update for something, the shift and the auto merger will come around the day after and bump the entire fleet to be up to date to those dependency versions. And the way we've done this is that we've actually had for each of we use different build tools or package managers like Maven or Pip and Yarn and whatnot. And for each of those, we have some sort of centralized way of saying that this is the version that we want in our fleet of a particular dependency, because that also takes care of dependency conflicts. So we can have like a known working set of dependency versions and then have that set of versions be applied to our fleet every day. It turns out to work really well. Yeah, and you can see security fixes and whatnot. And I'll actually show you a few examples. First, we can show this graph of, this is just the number of deployments that we do. I think it's weekly in this case. And you can see that the number of deployments that are started by a bot change is now roughly on par with the number of deployments that human developers Spotify do. And again, Google published a paper a bunch of years ago where they showed a similar graph, and in their case, the bots have pulled away from humans, and we expect that to happen for us as well. But for now, we're roughly keeping up. So this is a somewhat famous or infamous security vulnerability. I'm sure some of you had to deal with this. It was, I think, in November 2021. The Log4j vulnerability was fun. So this was just as we were rolling out fleet management for backend services. So the timing couldn't have been better for us. It was an excellent example of where we could actually try. Like, one of the reasons why we did this was, rather than having to put a lot of effort into upgrading our fleet in a very short period of time when we have a security vulnerability, we want to be able to do that in a few days. And here we got the excellent way of showing if we could. So what you can see here is the share of the fleet that has the fix for the Log4j vulnerability rolled out. And you can actually see that at this point, we were at roughly 80% adoption of fleet management. So about 80% of our backend services were sort of fleet managed. And for those, we were able to patch our entire fleet in less than 6 hours. And then for the remaining 20%, that still required a lot of engineering work. And you can see that that took multiple days to actually finish up. So this is exactly what we want to do. And we've been able to do a few more of these types of rollouts, or actually many of these rollouts since then, where we have some security fix that we want to get out, and we're able to get that out quickly. This is another way of looking at this. So this shows the time that it takes us to roll out. So we have an internal service framework, kind of similar to Spring Boot or whatever you would use to build your backend services. And this shows the time it takes us to roll that out to, I think it's 70% of our fleet. And you can see that the graph starts at roughly 200 days. So this was pre-fleet management. So it took 200 days to get organic adoption for a new version of the service framework. So the team who manages that framework would roll out the change, and then 200 days later, it would be at 70% of the fleet. And of course, in that framework, we roll out a lot of new features or performance improvements or reliability improvements or security fixes and all of those. And it would take almost a year to get to most of the fleet. And by automating that, we're now down to being consistently in doing that in a few days. And the reason why it's not just a day is that we don't do auto merging, as I mentioned, on weekends and Fridays and whatnot. So it takes us a few days on average. And this is where we want to stick. So that means now, if you're one of our infrastructure teams, you make a change to the framework or library or whatever it is you own and publish, you can have that being rolled out in the next day or two. This actually also means, this might look great, but it also means a big challenge for our infrastructure teams, because before they would get free QA by rolling things out slowly. So during those 200 days, people might report bugs and like regressions and whatnot, and they could fix those, and then they would slowly roll out. Now they can go from making a change to breaking all of Spotify in less than 24 hours. So this has required a lot of improvements in terms of test automation, in particular for our infrastructure teams. And that's a lot of our focus for this year, is actually to have our infrastructure teams being more confident with making these types of changes without breaking everything. So that's a lot of the focus at the moment. And I think this is the last graph I'm going to show. So this shows what's called repaving. So basically says what part of our components do we redeploy within a certain period of time. So the graph might be a bit hard to read, but the summary is that roughly 80% of all our components, this is not just backend services, but data pipelines, websites, and whatnot, we redeploy at least every 2 weeks. And redeploying things is a really good thing, because when you have things running for a long period of time, that's where you get, someone might make a manual change to that. So all of a sudden, the sort of source of truth that you have in Git is not true for whatever you run in production. You might have security vulnerabilities that remain because you haven't redeployed something. You might have fixed it, but you haven't actually redeployed it. So having this practice of repaving, this is a well-known good security practice, is great. So we're currently at 80%. The reason why we're not at 100% is that we still have some components that we haven't been able to onboard. And a lot of that is our sort of core infrastructure components, which we are also working on at the moment. And we have some weird ass components that have some legacy, so those also takes a longer time for us. All right, so lastly, I'm going to talk a little bit about what we're planning next. This is going to be fairly short, but so I already mentioned some of this. We want to make our tooling better. This is, I think, continuously true. And in particular, we want to make it easier for any engineer at Spotify to do one of these fleet-wide changes. I mentioned we have done 130 or so. I think, I might get this number wrong, but I think those 130 are coming from 80 or so different teams. And we want to grow that number to have more teams being comfortable in doing these types of changes. We want to make more and more complex changes. I also mentioned this before. So again, we're super confident at making config changes or dependency updates at this point. We're less confident at making complex code refactorings, for example, in a safe way that doesn't break in lots of edge cases. So we're sort of gaining confidence in doing more and more complicated changes. And lastly, as I already mentioned, we're going to try to remove that last 20%, so we're actually at 100% of our fleet. And I think this might be the last or almost last slide. We're also considering if this is useful for other companies and if we should release it externally. If you find that interesting, I would be super curious, so feel free to ask a question or come up after the talk, because every signal that we can get will help us in making that decision. This QR code will take you to, so we have, I mentioned before, Backstage, which is our developer portal. So if we would release this, we would probably release it under that umbrella of Backstage somehow. And the QR code goes to a roadmap update that we will give in a month or two on what the hell we're doing with Backstage going forward. So if you're interested in that, go for it. And lastly, if you found this interesting, we have published this in more depth. So there's a 3-part series blog post that we've done on our engineering blog, where you can learn about sort of the general stuff, what I've covered today in the first post. There's an entire post on the declarative infra stuff, which is pretty interesting if you want to sort of reconsider how you're doing that today, or if you're not doing it at all, this definitely presents a way of doing it. And lastly, one post that goes into the implementation of fleet shift and auto merging and all of those in much more detail than I could do today. Somewhere in there is also hidden an email address. If you want to reach out to the team, you can do that on that address. And lastly, we did a podcast episode. So if you hate reading and want to hear me talk more, that's one way of suffer for another hour. So you can do that if you want to. It's mostly of what I've covered here, although, of course, we didn't go as much into the implementation and whatnot, because all audio only. That is it. I have 20 minutes for questions. If anyone has any questions or thoughts, let me know. And yeah, again, thanks for coming.
For the teams that didn't have enough test automation, do you have dedicated QA test automation, or are you just forcing the engineers to learn how to test their own code?
Yeah, great question. So generally speaking, for most of our types of components, so backend services, data pipelines, so on, we typically don't do any manual QA. There are a few exceptions where we might have components that integrate with some third-party partner, for example, and we might need to go through a test protocol with that partner as part of some, something that is under PCI or something similar. That in that case we will do manual QA. The other exception is that for our mobile components, when we do a weekly release of our mobile apps, and that goes through a manual QA process as well. But generally speaking, we rely very heavily on test automation. Maybe it wasn't clear. I showed a graph of our this one. This shows the number of deployments that we do, and we do around 2,500 deployments per day. So it would require a lot of testers if we would do that with manual QA. So that's why we rely so heavily on test automation for where we can.
So you said that every team has ownership of their own components and then test their own components. But often it happens that when you put a lot of components together, that communication between them and so on results in integration errors or misconceptions between teams and so on. So how is your experience with testing after the team itself has completed their own testing, and with also these big changes that you make? So how many errors happen in the integration in the system as a whole?
Yeah, it's a great question. Unfortunately, I'm not going to have a I might have a surprising, but maybe not a good answer. So what we do is that we focus quite heavily on integration testing as part of the CI build. And typically what we do is, I'm going to probably overuse backend services as the example here, but if we use that example again, if you take your backend services and you actually, as part of your CI testing, you spin that up with mocked dependencies around it. So if you're dependent on some other services, you will mock those out, and then you will issue a bunch of API calls as part of your testing and then make sure that works. What we don't do a lot of, we do in some rare cases, but not a lot, is things like contract testing. So we actually don't test this graph at all, basically. And that was where I said it's surprising, because I would imagine that we would see a lot of failure cases where we would just, break backwards compatibility for some API or whatnot. But we actually have very, very few of those types of failure cases and incidents. We do have strong conventions and rules around how we design APIs to be backwards compatible and whatnot, but I would still, naively, I would expect this to break more than it does. So because of that, we haven't actually focused too much on like contract-driven testing and things like that, because it just works. But and this is where I'm saying my answer is not a particularly good one. We don't actually know exactly why it works, but it works surprisingly well. To maybe the slightly less tongue-in-cheek answer to that is that I think this is an area we should probably invest a bit more into and get better testing and better real integration testing, like how components talk to each
other. Hello, just a quick question. You've mentioned changes about YAMLs and structure stuff. Wouldn't it make sense to have them in a separate repo, for example?
Yeah, so we do that as well in some cases. So to take an example, we deploy all our backend services into Kubernetes. We have we've had, I should say, we're actually moving away from that in this part of the answer. We've had all the definitions of, the namespaces, the quotas and whatnot have been in a single Monor repository. And that's been great to be able to make some of these changes. Unfortunately, it sort of breaks our ownership model, because then there's some team that has to take ownership for that Monor repo, and that Monor repo turns into a mess because you have hundreds of teams contributing to it. So we have to have very strong validation, test suites for that and whatnot. So typically what happens is that we start up with that approach, and then we discover after a few years that no, we actually want to move this closer to the code that it belongs to. So for that particular monorepo, that work is happening as we speak. We're splitting that up, and we're moving like namespace declarations for specific components to the repository for that component. But it's a trade-off. So in some cases, we have a single big repository for everything, and we can make atomic changes within that repository, still with a controlled rollout. And in most cases, we have found that the way we work with our ownership model, it works better to have basically everything live as close to the code of that thing as possible, because that's where it's getting best maintained. And then we have to apply this type of solution in order to, for example, the example I showed of like optimizing autoscaling. We have to use something like this. So it's a bit of it's definitely a trade-off. And I think if we would imagine a world where we would be fully in a monorepo, I think we could actually achieve both of those, because then we could have like Kubernetes configuration live together with the code that it belongs to, but still be in a single repository. So that's one of the trade-offs that we're debating at the moment. It's a great question. It's a very nuanced question. It's not as easy as it might seem.
Say you have one of these shifts, and you get all these PRs. Some of them may merge, and this change gets deployed.
Yep.
And it starts failing. Yep. Is there any way that you catch that and then flag the shift as like, okay, this is bad, don't continue with this, like stop the other PRs from merging?
Yes. So yeah. So in here, sorry, I skipped over this. So it's a good point. So in here you can see there's a box in the middle that says Firewatch. So that is exactly that thing. So Firewatch sits and watches all of these shifts as they are rolled out, and provides monitoring for the author, the change author, so they can then pause the rollout. We haven't automated that yet. That is actually work that is ongoing to automate that, to automate the pausing, I should say, or like pacing of the rollout. But yeah, it's something that Firewatch offers today. And as I said that, I realized another thing that I sort of skipped over was that I mentioned that we have this, like we have all these components and we have strong ownership for them. We apply that to shifts as well. So a shift is just another type of component, and it has an owner. So every one of these 130 something shifts that we've done has an owner, and as a change owner, they are responsible for monitoring the rollout and taking care of the bugs and the edge cases that they find during that rollout. So that's part of this process as well. More questions. These are great questions.
I would like to ask that for every team or squad, when they adopt this fleet thing, they need to do some work to conform to these protocols. Are there any teams that has like really strong pushbacks that okay, we don't want to do this, we want to manage it completely our own? Or like most teams are just happy to accept these changes?
So there were a few teams initially. Let me say it like this. There were some teams that we allowed to opt out components from being fleet managed, and typically the types of components that were opted out initially were those that were under some particular regulatory requirements. So again, PCI, ITGC, something like that. We're not in a heavily regulated business. Some of you might be. So that's a small share of our fleet that has those types of regulatory requirements. And initially, we couldn't support them through fleet management. So they had to opt out. Since then, we've actually fixed that. So now you can do that and be compliant. So now we're actually managing those as well. And then to your actual question, yeah, so there were a few teams that opted out things. Typically, they wouldn't opt out all their stuff. It would be more like a few components that were in a particularly bad shape, and maybe they were decommissioning those components in a month or 2 or 3. So rather than fixing the test automation for them. They just wanted to decommission them instead. And there were a few, not that many, but there were a few teams that had strong opinions initially, but I think most of those have removed their opt-outs now because they're seeing the benefits that they're getting. So I'm not exactly up to date. We might have a few of those holdups still, but largely, like, I'm going to say 99% of our teams and developers are happily opting in their components. But we did, yeah, so maybe I should have explained this as well. So what we did was, typically when we roll out new infrastructure at Spotify, we do that opt-in. So we say, hey, here's a new great product that our infrastructure team is offering. You can use that if you want. And we want to have that mechanism because that forces our infrastructure teams to build good products. If they build crappy products, no one will use them and they won't be successful. So we actually normally want to have that opt-in type of process. With this stuff, we actually took the opposite approach and we said, we're going to opt in everyone. And if you're not okay with that, you have to explicitly opt out. So you could opt out. The opt-out was a self-service, like you just added yourself to a file in Git somewhere and your component was not going to be fleet managed. But if you didn't, at some point in time, you're going to be fleet managed no matter what. And that's a very, very unusual approach at Spotify. And we did it in this case just because the type of things that we wanted to solve, like being able to do security fixes much more effectively and so on, were so important that we were actually willing to sort of take the downsides of having that type of approach. Yep.
Looking at your interesting dependency graph, in my experience, whenever you do something extreme, like using any good design pattern or practice, whatever, if you take it to extreme, it can be dangerous because the drawbacks tend to outweigh the benefits. With that in mind, do you still think going microservices and small independent components and all these things is the way you would do it if you would redo the whole thing? Or have you learned something about microservices and architecture and so on the way?
Yep. It's so this is very core to my job day to day, this type of question. So the short, easy answer would be that yes, we still think this is the right approach for us. And I'm boldly gonna claim that I think once you're at a scale with hundreds of, like we have maybe 600 teams or so at this point, and we're building one product. That's an important part to sort of understand about Spotify, is that we have one product. So all of these 600 teams essentially work on the same thing. Like you might be on the edge of that product, you might be working on, some payment system or whatnot that is not like maybe perceived as core of the audio streaming experience, but you're still like on that same big product. So it's not that we have a bunch of different siloed parts in the company. Everyone's collaborating on the same thing, which is also why you're seeing this highly connected graph. And I think in that context, you have a large organization, you have a lot of traffic like we do. We get several million RPS to our services around the clock. So in that scenario, I actually think this architecture makes a ton of sense. There are many of these other scenarios where you're a very different company, and I think this architecture might make much less sense to you. But for us, I think yes, it still makes sense, and we're not aiming to make those types of changes. There are definitely changes that we want to make to our architecture. So for example, when you look at this graph, you could imagine it would make sense to have a little bit more well-defined subsets of the graph that we could reason about independently and maybe have more loose coupling. So you could pull out pieces and treat them independently. We're not really able to do that because it's so highly connected at the moment. So we're doing some work around structuring things into domains more clearly and maybe introducing architectural constraints that will limit exactly how this dependency graph can look. But the small components, the strong ownership practices, I think we will keep. for a while. So it's a great question, and like it's very top of mind for us all the time to sort of question what the hell we're doing.
Hey,
Hey.
so my question kind of ties into like regardless of the culture and how strong the culture in terms of technical maturity is in any organization, you will have to deal with various levels of maturity in these teams. And you guys are running like some self-sufficient teams, and you were mentioning ownership. Are these teams also owning the risk tolerance or the risk level that they expose themselves via this like certain level of automation?
Yes, they do. So in the end, they are fully accountable for their components. So yeah, that includes that as well. So that was, again, one of the reasons why we offer this opt-out possibility for fleet management was like, if you have typically would be like a component that were particularly critical and in a particularly bad state. That would typically the combination where people will opt them out, and they would need to fix the bad state part of that. But yes, teams would need to do that assessment on their own and take accountability for those decisions. Sorry? You mean fleet management? Yeah, so you could yes, you could say for your component that my website is not going to be fleet managed. That opt-out had a deadline, so like in 6 months you would have to reassess it. But yes, that was completely self-service and up to each team if they wanted to do it. In reality, I think I might lie now, but I don't think we ever got over like having 1% of our components being opted out. So it was fairly few that were opted out, even at the midst of the rollout.
Hi, one question would be how you work out this with breaking changes, because probably they will exist.
You mean in this graph?
Or does the fleet management also work with breaking changes? Because automation and breaking changes is probably not a good fit.
Yeah. It's an awesome question. It was part of the reasons why we wanted to do this to begin with. So, and again, if we look at this graph, this again happens to be backend services, but you can apply this to any other type of component. Each of these services offers some sort of API. Like each of the edges in this graph shows someone using the API of a different service. So I mentioned before that we have strong conventions around how we do API design so that you can make non-breaking changes to your APIs, but every now and then, to your point, you have to make a breaking change. And that is super painful. So the way we do that as much as, and this is not unique for us, I think it's generally a practice used, is that when we need to make a breaking change, you typically need to well, obviously you need to offer whatever your API users are supposed to move to, and then you can make the switch, and that's where fleet management comes in. So we can identify the sort of call sites for your API, which services are calling your API. And then in some cases, again, this goes into that making complicated changes challenge that I mentioned before, but if those changes are doable to author a shift for, then you can do that. And the way I mentioned that Google paper before, and they reason around the same thing. Typically what you find that you need to do is you can't make a complicated API change in one atomic change. So typically you have to do it in multiple steps. And then the API publisher will need to expose APIs that allows for that gradual shift over. So basically you need to design your API change in a way that is automatable. And this we've only so far done for a limited number of cases. So it's not something we have a ton of experience with, but it's exactly one of those things that we want to learn and get better at going forward. Cool. I don't know where we are on time. 1 more minute. Last question.
Just a quick question about this graph. How do you find dead branches on this? Like services that are part of features that are no longer used? Maybe them have traffic by themselves, but they are dead in general.
Yep. So the short answer is poorly, I think. So that is something that we want to get better at. And what we have, one of the things that we're lacking today is so this again shows dependencies within our backend ecosystem. I could show you a similar graph for dependencies within our data ecosystem and within our client ecosystem. What we lack is a good understanding of how those fits together. So for example, in our case, because so much of our API traffic comes from our clients, the most important thing to look at would be the dependency graph between clients and backend. But we basically lack that instrumentation today. So we can't actually answer your question in a really good way today. What we can do is to look at sort of more naive signals of like what's the RPS the service gets. And because we have all of this in BigQuery, as I mentioned before, we can actually do pretty advanced analysis on top of that using like normal graph analysis algorithms. So that's ways that we can identify, I'm going to say, candidates for dead parts of this graph, but it's not particularly precise, and it does require a fair amount of manual human analysis to do that today. So that is something we want to improve, and in particular we want to improve this like understanding of some feature in our clients. What does that call into in this graph? And that's a bit of a blind spot to us today. Cool. You had a lot of good questions. I'm going to stick around for a few minutes, so feel free to come forward if you want to chat more. Otherwise, thanks a ton for coming and thanks for the questions.